Aspirations, a quote by Gary
ஐயோ
Hamel.
இதோ
Day 2 of
ஆயிடுச்சு.
the webinar series, Selected Topics in Chemistry for
தெரியல.
CSIR NET Set GATE IIT JAM aspirants is an effort to help you accomplish your goals. On behalf of the Department of Chemistry, I welcome our principal, Dr. R. Shanti, to the webinar, whose presence has greatly boosted our morale. I welcome Dr.S.Kabilan, former head and professor, Department of Chemistry, Annamalai University, to present on the topic Retrosynthesis. Thank you, sir, for graciously accepting our invitation to share your expertise. I welcome all the participants of this webinar, including students and faculty from various colleges and universities. Those of you who have joined us through the Google Meet, as well as those of you who are watching the live streaming on the YouTube platform. We are elated by the feedback we received for yesterday's talk on spectra of metal complexes by Professor S. Srivatsan. Participants had posted their compliments, indicating that it was an excellent, informative session. May I request Mrs. T. Shobna Premlata, Assistant Professor, Department of Chemistry, to introduce the speaker to us.
Thank you, Priya. Audience, kindly mute your audio. I deem it an honor to introduce Dr. S. Kabilan, former head, Department of Chemistry, Annamalai University, to this August gathering. Dr. Kabilan has 31 years of teaching and research experience. He has more than 110 publications in peer-reviewed international journals and 2 publications in national journals. He has published 2 books. Sir has received grants worth of rupees 1 crore 37 lakhs 65,000 for 4 major projects and 2 minor projects. Currently, he is working on a major project worth of rupees 27 lakhs. Dr. Kabilan has guided 30 PhD scholars, 27 have been awarded their doctoral degree, 3 scholars are pursuing the research, and 31 students have completed their master's and MPhil program under his guidance. Sir has organized 2 national and 2 international conferences and attended 51 national, 13 international conferences. He has also attended numerous seminars, symposia, and workshops. Dr. Kabilan is a member, Board of Studies, Annamalai University, and also a member of Indian Council of Chemists. Sir is keeping himself busy by delivering webinar for the benefit of the students who are aspiring for their higher studies. We are indeed privileged to have you, sir, with us this morning. Over to you, sir.
Thank you. Presentation.
Sir, Dr. Kabilan, sir,
Yeah.
you may start, sir.
Yeah.
You can present your screen also.
Yeah.
Sir?
Screen share.
Yeah, he's sharing,
You have
ma'am.
to give the screen
Yeah,
share.
okay, ma'am. Yes, ma'am. I was not able to view. Okay, ma'am.
Yeah, yeah.
Okay.
You give the screen share. Present now. Can you see our screen? You better. The screen
No,
share.
sir. No, sir.
Participants, please do not present your screen. It will interrupt the presentation of the speaker.
Prema, please stop presenting your screen. Priya, ask sir whether you're not able to see.
Sir, Kabilan sir. Kabilan sir. Kabilan sir. Sir, can you present your screen? Ma'am, Shanti ma'am, if you have his number, can you just ask him, ma'am? Because I think he's not responding on this G Meet. Shanti ma'am? Shanti ma'am?
Yes, sir. I'm just trying his number.
Ma'am, sir has started, ma'am.
Okay.
Welcome, sir. Good morning. Ma'am, I think it is started, ma'am. Sir, it is not audible to us, sir.
Wait a minute. Can you see the PowerPoint?
Screen is visible, sir, but audibility.
Can you see the PowerPoint now?
Yes, sir, we can see the screen, sir. We are not able to hear you very much, so.
No.
Sir, the voice, is there any way you can increase the volume, sir? Because we're not able to hear you clearly, sir. Screen is visible.
Can you hear me? No.
Actually, the voice is a bit faint, sir.
Wait a minute.
I think volume, if you can adjust the volume, it should be fine, I think, sir.
Volume is full here. Can you hear me now? Can you hear
Yes,
me?
sir. Yes, sir.
Yes, sir.
Okay.
Yes,
Okay.
sir. No,
Okay.
so fine, sir. Now
Okay,
fine,
ma'am.
sir.
Okay.
Thank you, sir.
Okay. Let me start now. Thank you for having given me a chance to be amidst you. The first thing is this is designing of organic synthesis. Organic synthesis having several nodes and needs. And for any CSCR aspiring student, there are nearly 14 units in organic chemistry and 4 units in general chemistry. And out of which, studying the organic chemistry in a different fashion will help them. Ma'am, can I go bilingual or can I go only in English?
Any bilanguage, it's your choice, sir.
As you please. My choice is different, madam. Student choice
No,
is
sir.
important. You
They
tell me.
will.
Okay.
Okay, sir. Okay, sir.
Do you want to be in bilingual or do you want to be restricted to be in English?
Bilingual also. Okay. Bilingual, sir.
Okay, ma'am. Designing organic synthesis having its own value. Let me go directly. Suppose if you are having what we are now dealing is nothing but a mathematics in organic synthesis or organic chemistry. And if any student is capable of learning this efficiently, I have in this more than 16 lectures. All the 16 lectures will lead to a pass in CSCR. No other subject is needed for study. That is one point I want to say now. Now this alkaloid is a very big molecule. And if you look into the literature, it is having nearly 52 steps for its synthesis. But using a different approach, which is called as a synthan approach. In this approach, what we have to do is, we have to cleave the covalent bonds of the given molecule. This is the target molecule. The target molecule here is one whose synthesis is being planned. Any MSc student after completing his MSc wants to go any pharmaceutical industry, which is lucrative now. And if he goes immediately, he will be given a task of a simple molecule like this. This is not a simple molecule. and they have to write the synthesis of the molecule by designing the starting material going from the product. This product is called as a target molecule. This target molecule can be very easily lead towards the starting material. This is reverse of a synthesis, what is called as a retrosynthesis. In this, you know very well covalent bond is having two electrons, and you can cleave at any point of the target molecule. You can get certain precursors. Precursors என்னன்னு கேட்டா precursors வந்து ப்ராடக்ட் வர்றதுக்கு ப்ரீவியஸ் ஸ்டெப்ல இருக்கிறது வந்து precursors பேர். After getting the precursors, even one of the precursors may be a toughest molecule. You can go again by just modifying the molecule by writing a single symbol called retro. Retro means going back in organic synthesis. Likewise, the molecule which seems to be very difficult at first, don't worry about what I have written. Since I know all the mechanisms to leading towards the target molecule, I have written very easily. So you have to analyze a molecule. This is called as a scanning of the given product. After scanning the product, which seems to be very difficult if you go into the IL Phenol or Murray or whatsoever the book that you are dealing for synthetic organic chemistry, Indian or foreign, that may lead to several steps. Even without understanding the steps involved in it and the reagents in it, the students are mugging up and just vomiting in the paper. Instead, you have to see the molecule and you have to just where we can cleave and get the precursors is the point. After getting the point, one of the precursors may be so tough and that can again be cleaved or modified to get a simplest starting material. This part of the program in Synthan approach. Synthan is nothing but, I will tell you the definitions later. It is a reverse of organic synthesis, not from the starting material to the product, but from the product to the starting material, the simplest possible way in which the known mechanism is already existing. And we have to concentrate on more yield and also less number of steps. That is the point. In this, we are having two aspects. One is called as analysis, another one is called as a synthesis. The same molecule which I have got as the final product in this, I can start with that in the synthesis. In the retro having the symbol, you look at it, two lined single arrow. But in the case of synthesis, you have a single arrow. And start from that and go for simply managed reactions followed by a Michael reaction. And then you can reduce and alkylation and followed again by a managed reaction followed by a Michael reaction. You will get this. In this reaction, what you are having is only managed and Michael. Within 4 or 5 steps, you look at that 1, 2, 3, 4 steps only, you are getting the molecule, which seems to be very difficult at first sight. Okay, if you look at it in the first sight, it's a very difficult molecule. But using this approach, you can very easily decipher the particular problem and get into the starting material. From that, you can design a synthesis without much ado and difficulty. Okay. And how to learn this particular way? There are simple definitions. One is called as a disconnection. For I will take some simple example. If you want to have a tertiary butyl alcohol as the target molecule, you cleave the COH bond and get certain positive and negative species. These positive and negative species are called as synthan. Synthan is nothing but a charged species getting out of breaking a covalent bond in a target molecule. Then you have to look for the easy starting material. This easy starting material is tertiary butyl chloride. Look at it, you know that tertiary butyl chloride, just SN1 reaction, you will get a tertiary butyl alcohol. But at the first, in systematic manner, in a conventional way, if you are looking into the book, they will start from tertiary butyl chloride and any base, you will get a tertiary butyl alcohol. But you have to go in this way. This approach, having a two-line single arrow, is called a Synthon approach. Disconnection is nothing but breaking a covalent bond, not using a chisel and a hammer, but by your chemistry mind, where you know very well that a bond is made up of two electrons. Catalytic cleavage makes one part into a negative charge, another part into a positive charge. Then getting the equivalent for the synthon is called as a synthetic equivalent. You get a generalized fragment, usually an ion produced by a disconnection. And synthetic equivalent is nothing but what is the equivalent for the synthon, you get it. And after that, you have a reagent. Reagent is one which is capable of giving the particular synthon in solution. And FGI, I will come to you later. The target molecule is one whose synthesis is being planned. ஒரு ஸ்டூடெண்ட் இப்போ வந்து ஃபார்மசூட்டிக்கல் இண்டஸ்ட்ரி போறாருன்னா போற ஸ்டூடெண்ட்டுக்கு வந்து முன்னாடி மாதிரிலாம் கிடையாது. They will ask they will give some simple molecule and then they will ask the student to synthesize it. Okay, that's the first point. அதுக்கு எப்படி ரெட்ரோசிந்தசிஸ் எழுதுவீங்க அப்படின்றது தான் முக்கியமான பாயிண்டா இருக்கும். ஒன்ஸ் வந்து ரெட்ரோசிந்தசிஸ் ஒரு ஸ்டூடெண்ட் வந்து லேர்ன் பண்ணிக்கிட்டாருன்னா then he is capable of writing the synthesis for any molecule at any point of time, and he can develop his own synthetic methodology, and he will satisfy the manager of the particular company R&D division, and he will gain a lot. That is the point. So now the conventional way of organic synthesis is now getting dwindled, and it is no longer, it will be an obsolete one sooner. இதுல டெஃபினேஷன்ஸ் வந்து ரீஏஜென்ட் சொல்லிட்டேன். ரீஏஜென்ட்ன்றது என்னன்னு கேட்டா, இந்த டெர்ஷியரி பியூட்டைல் குளோரைடு இஸ் ரீஏஜென்ட் ஃபார் திஸ். இந்த சிந்தான்னு வருது இல்லையா, ஒரு பாசிட்டிவ் நெகட்டிவ் சார்ஜஸ், சிம்பிளா சொல்லியிருக்கேன் நான். இதுக்கான ஈக்குவலன்ட் வந்து சிந்தட்டிக் ஈக்குவலன்ட். அதுக்கான ரீஏஜென்ட் என்னவோ சோடியம் ஹைட்ராக்சைடு போட்டு இப்படி வருவோம்ல, அதான் ரீஏஜென்ட் பேர். இது சிம்பிள் டெஃபினேஷன். டார்கெட் மாலிகூல்னா உங்களுக்கு தெரியும். டார்கெட் மாலிகூல்ன்றது ஒரு ஃபார்மசூட்டிக்கல் கெமிக்கலா இருக்கலாம், அல்லது சிம்பிள் கெமிக்கலா இருக்கலாம், உங்க எம்எஸ்சி சிலபஸ்ல வரதா இருக்கலாம், லைக் மார்பின், codeine, or even a vitamin A or vitamin B or vitamin D or vitamin H எது உங்களுக்கு கொடுக்குறாங்களோ அதை நீங்க கன்வென்ஷனல் வேல போகாம நீங்களே வந்து ஒரு சிந்தட்டிக் வேல வந்து சிந்தசிஸ் நீங்களே டிசைன் பண்ணலாம். அது லேர்ன் பண்றதுக்கு முன்னாடி 2 எக்ஸாம்பிள் சொல்றேன். One example is what I have chosen from this. I have chosen from the book called E.J. Corey. அவர் ஒரு 10,000 மாலிகூல்ஸுக்கு வந்து pharmaceutically important மாலிகூல்ஸுக்கு வந்து he has given retrosynthetic analysis in a special book, Designing Organic Synthesis, a logical way ன்னு சொல்லிட்டு ஒரு புக்கு. அது வந்து 2009ல வந்தது. That book I am having. From that I am choosing these things, choosing all the examples. இந்த எக்ஸாம்பிள் எடுத்துட்டீங்கன்னா PHCH2 CHCOET ஒரு சிம்பிள் மாலிகூல் உங்களுக்கு கொடுக்குறேன். நீங்க ரெட்ரோ பண்ணும்போது ஃபர்ஸ்ட் அனாலிசிஸ்ன்றது உங்க குழந்தை கையில வந்து ஒரு சாக்லேட்டை கொடுத்துட்டீங்கன்னா சாக்லேட்டை தவிர உங்க ஃபேஸ்லாம் பார்க்காது. அது மாதிரி if your target molecule is given to you for a synthesis, you have to look into the target molecule where we can break and get the starting material. அதுக்கு அனலைஸ் பண்றோம். அனாலிசிஸ் இஸ் நத்திங் பட் லிசனிங், அதான் அர்த்தம். கான்சென்ட்ரேட்டட் அப்சர்வேஷன் அண்ட் அனாலிசிஸ் இஸ் கால்ட் as a listening. அதை பண்றோம். இதுல ஏல பிரேக் பண்ணலாம், பில பிரேக் பண்ணலாம். ஏல பிரேக் பண்ணீங்கன்னா உங்களுக்கு தெரியும், இந்த பக்கம் 2 எலக்ட்ரானை எடுத்து இங்கே போட்டுட்டு இங்கே பாசிட்டிவ் சார்ஜ் கொண்டு வரலாம். இதான் சிந்தான்ஸ்னு பேர். இதுக்கு சிந்தட்டிக் ஈக்குவலன்ட் என்னன்னு பார்க்கலாம். பி வழியா கிளீப் பண்ணீங்கன்னா இங்க வந்து பாசிட்டிவ் போட்டு இங்க நெகட்டிவ் எழுதலாம். இது ரெண்டுல எது லாஜிக்கலி பாசிபிள்னு நீங்க திங்க் பண்ணும். லாஜிக்கலி பாசிபிள்னா இது டயத்தில் மேல்னேட் வந்து உங்களுக்கு ஆக்டிவ் மெத்திலின் குரூப்ஸ்னு பேரு. இது வந்து உங்களுக்கு ஆல்ரெடி ஸ்டோர்ல இருக்கக்கூடிய டயத்தில் மேல்னேட் இருக்கு. CH2க்கு ஒரு பிஆர் அட்டாச் பண்ணீங்கன்னா PHCH2Br வரும். ஒரு SN2 ரியாக்ஷன்ல ரொம்ப ஈஸியா கொண்டு வந்துடலாம். பட் இந்த பக்கம் நீங்க கிளீப் பண்ணீங்கன்னா PH+ வருது. PH+ வந்து உங்களுக்கு தெரியும், அரோமேட்டிக் ரிங் சிஸ்டம் இஸ் ஹைலி எலக்ட்ரான் ரிச். அதுல வந்து PH+ போட்டு நம்ம வந்து ஒரு சிந்தட்டிக் ஈக்குவலன்ட் தேடுறது வந்து தேட முடியாதுன்னு இல்லை, தேடுறது வந்து இல்லாஜிக்கலா இருக்கும், ஈல்டு கம்மியா இருக்கும், ரீசனபிள் மெக்கானிசம் இருக்காது. So even for designing an organic synthesis in analysis by cleaving the bond called disconnection, you have to look into the following details. Logically, இது பாசிபிளா இல்லையா? இப்ப இது லாஜிக்கலா பாசிபிளா இருக்கிற மாதிரி இருக்கு. ஸோ அனாலிசிஸ்க்கு நம்ம என்ன யூஸ் பண்ணோம்? டபுள் ஹேண்டட் ஏரோ போட்டிருக்கோம். சிந்தசிஸ் டிசைன் பண்ணலாம். சிந்தசிஸ் எப்படி இருக்கலாம்? டயத்தில் மேல்னேட் எடுத்துட்டு ஒரு இத்தாக்சைடு பேஸ் போட்டோன்னு வச்சுங்க, இந்த அசிடிக் ஹைட்ரஜனை எடுத்துடலாம். எடுத்துட்டு கார்பன் அயான் ஜென்ரேட் பண்ணலாம். After generating the carbon ion, you can go for a CH2Br SN2 reaction. You will get target molecule. Target molecule is one whose synthesis is being planned. இது உங்களுக்கு சொல்லிட்டேன். இது ஒரு எக்ஸாம்பிள். எக்ஸாம்பிள் நம்பர் 2 போறோம்னு வச்சுங்களேன். If you go for example number 2, இது வந்து ஒரு 6-member ring with a double bond இருக்கு, with an anhydride group இருக்கு. இதை பார்த்த உடனே நம்ம ஒரு கெமிஸ்ட்ரிக்கு என்ன தெரியும்னா 6-member ring with a double bond can be deciphered using Diels order reaction. ஸோ என்ன செய்யலாம்? நீங்க அனாலிசிஸ் பண்ணலாம். அனாலிசிஸ்ல ஆப்போசிட் த டபுள் பாண்ட் இருக்குல்ல, 6-member ring டபுள் பாண்ட்ல நீங்க இந்த பாண்டை சைமல்டேனியஸா கிளீவ் பண்ணலாம். யூ கேன் கிளீவ் இட் அண்ட் யூ கேன் ப்ரொடியூஸ் அ டைன் அண்ட் டயனோஃபைல் கொண்டு வரலாம். இதுக்கு ரெட்ரோ டீல்ஸ்ன்னு மேலே எழுதிக்கலாம். ஸோ யூ காட் எ டைன். இந்த 2 பாண்டையும் கிளீவ் பண்ணிட்டீங்க. இந்த பாண்ட் இங்கே வந்துடுது, இது இங்கே வந்துடுது, இங்கே வந்துடுது. ஸோ யூ கெட் எ டைனோஃபைல் வரும். இந்த டைனோஃபைல் வந்து
sorry sir, sorry to interrupt sir. Sir, live streaming is going on, so they're saying if it is in English will be better, we'll be able to understand better, because West Bengal.
Fantastic.
Thank you sir. Sorry sir.
No problem. So if you look into this this particular product, if you go look into this particular target molecule, this is having a six-member ring with a double bond. When you're having a six-member ring with a double bond, it is better we have to go for the deals or a reaction. If you go from the product towards the reactant, it is called as a retro deals. In this, opposite to the double bond can be disconnected, and you will get a diene and a dienophile. And dienophile, you know very well, it is nothing but a maleic anhydride. If you have a maleic anhydride here, and it is available in your stores also as a white powder and diene also, and you can go for the synthesis you can design in a single barrow, and this deals on a reaction at 90 degrees centigrade, you will get the product. Okay, a molecule is, this can be given to your MSc students also as a small problem. Similarly, as a tutorial is nothing but a problem is given and solved by a teacher. If a problem is given in the similar fashion, the student is capable of solving it immediately, is called as a tutorial. I give this problem as a tutorial. Here also you have a bicyclic compound and also having a six-member ring with a double bond. In the similar fashion, you can just cleave these two and convert into diene and a dienophile. On this part, you will get a furan. This part is acrolein. Acrolein you can very easily get by adding a drop of sulfuric acid over glycerol. That's a +2 level reaction. Students are very aware of it, no problem at all. Now, in analysis, you are looking at, I'm just using double-lined single arrow. Synthesis in Synthan approach, just to take furan, which is a solvent, and you have an acrolein, and just to have it, you will get the product. A bicyclic compound, which seems to be difficult, which is a precursor in some other reaction, where you will be getting a large, big molecule, even for the vitamin A, and this molecule can be synthesized very easily using this approach. How to learn? So we have to learn. There are the nearly 8 lectures we have to study, in which one is called as a one group disconnection. Since you are given 1.5 hours of time, I feel I am afraid that I cannot complete all these things. Even then, I will try to give the glimpse of the approach of it, or we can say the tip of an iceberg only I can show. Here, the disconnections of alcohols. One group means compounds which are having only one functional group. In that, which we have to study first is called as a disconnection of alcohols, as alcohol is a functional group, primary, secondary, tertiary, whatsoever the case, even acetal, ketols, etc., and also cyclic ethers. Retrodyl sort of reaction, disconnection of olefins, disconnections of carboxylic acid, disconnections of aromatic ketones, disconnections of alkanes. So these are all involved in the one group disconnection. The book which I am also quite often referring is called as Stuart Warren, who has written 2 books. One book is his own hand notes. That notes happen to be my collaborator. I got it from him directly. And from that, I have chosen certain examples for the study, for particularly for MSc students. We will start with disconnection of alcohols. If you look into this target molecule, you have to take it as an alcohol. You have to take it as an alcohol. And what you have to do is you have to scan the molecule. You're having 2 alkyl groups and 1 cyano groups, 1 CH, 1 CN. It's a tertiary alcohol. What you have to do is you have to disconnect the easily leaving group called CN, and you will get CN negative, and you get synthetic, that is synthans. I know I told you already what are synthans. Synthans are nothing but a positive and negative species gone out of cleaving a covalent bond in an organic molecule wherever and whatsoever it is having. And I got it. I just removed the proton and got the ketone. So on seeing this starting material, you are very familiar. It is nothing but the cyanohydrin formation of a ketone or an aldehyde. But at the first sight, it makes you some confusion. What is this molecule? But I told you we have to study in terms of alcohol. So we are just seeing in terms of alcohol. You have 2 alkyl groups and 1 CN and OH. Among them, the CN is best leaving. And I just cleave that. I got a CN negative and I got the ketone. The synthesis is so easy, you know very well. Nothing but cyanohydrin formation of a ketone. Okay, this is one thing. And if you go for the second, I will give few examples only. I'm just leaving several examples. I got more than 1,000 examples to write for a starter who is very much interested in knowing this. There are several things they have to work on their own by making a slate and a pencil. Here also, you have to consider this as an alcohol. You have a phenyl and methyl and a carbon and a tertiary alcohol. I can just cleave C and acetylene. I'll get acetylide anion. And here also I will get a positive charge. I just removed the proton and got the astrophenone. Now this is in the synthesis part, acetylene and sodium liquid ammonia. I can generate HC triple bond C negative and just add astrophenone. It is nothing but the nucleophilic addition of the electron deficient carbonyl carbon. I will get the target molecule very easily. Likewise, I just leave this. Uh, Here also I'll just leave this. So if you look into the alcohol having very similar alkyl groups, you can cleave the alkyl groups simultaneously. You can cleave the alkyl groups simultaneously, and if you cleave the alkyl groups, you will get CS3 negative ions. What is the equivalent for CS3 negative ion? The Nobel laureate Grignard had developed a Grignard reagent where you get methyl magnesium bromide and rest of the molecule, while you are cleaving the two negatively charged part from a carbon, tertiary carbon, two negative charges were removed. So you have to incorporate for the valency satisfaction two negatively charged atom in our periodic table. That is nothing but an oxygen. So ethyl, already one carbon is there. And I introduced one oxygen for the two negatively charged removal. Already one oxygen is there. And I removed the proton. I put the methyl or ethyl group. So I got an ester. I know very well from the basic organic chemistry. If you are capable of, from the Grignard reactions, if you are capable of adding to the ester two Grignard reagents at a time in a dry ether or a THF, and you will get a tertiary alcohol with these two similar groups as alkyl. So if you look into synthesis, I got this CH2COO2H5 and one first methyl magnesium iodide in dry ether, nucleophilic addition. I will get that on hydrolysis. I can go for hydrolysis or need not. I will get ethyl methyl ketone and one more methyl magnesium iodide. I will get the second methyl group is being attached on hydrolysis. I will get the target molecule 6B. This is the 6B. So the point is, in higher order synthesis, in certain cases in alkaloids, steroids, vitamins, and pheromones, etc., in certain ring systems, you will be having two similar alkyl groups with an alcohol. How to synthesize? Just cut short in the similar way using the synthan approach. Simultaneous cleaving of the two similar groups leads to two alkyl groups with a negative charge. This is called as a synthan. What is the synthetic equivalent for that? In CSIR syllabus, they will give certain synthons like CS3CO plus, CS3CO minus, CS3 minus, pH minus, and CS3COO, CH2 minus, like that. And you have to identify what is the equivalent for synthon, what is the actual reagent for synthons. That on a period of time, and if you study on your own by seeing the books, of course, no book is available now to learn this, but it is a fantastic technique. And you need not mug up any one reaction or a mechanism or even a reagent or a rearrangement, whatsoever the case. On seeing the molecule, you can just scan it and you can simply write the synthesis within no seconds. So that will come if you are practicing and practicing and practicing well by means of choosing certain problems on your own, particularly starting from alcohols. So I got it two alkyl groups negative charge. The equivalent for this is magnesium, methyl magnesium bromide. Two molecules at a stretch. I will get the product. Okay. This is quite interesting. This particular also you have to look not as a 6-member ring with a double bond. Of course, you can go for it. And you look it as an alcohol. What you do is two similar groups are attached first. And what you have to do first is first cleave in the retro deal sorted manner. And you will get you just cleave two molecules. You just forget it in a different fashion I have written. You just cleave these two phenyl group. You will get two phenyl pH minus. For that you write equivalent pH MgBr. Rest of the molecule is ester. I told you when two similar groups are attached and these can be cleaved in a single fashion, and you will get that, and two negative charge were removed. So you are introducing one oxygen in this carbon, then removing the hydrogen and converting into an ester. So for this, you can go for deal sorted because you are having an electron withdrawing group. This is a stereo selectivity or stereo, that is stereo environment requirement for any Diels order reaction is the diene and dienophile. The diene should have a electron releasing group and the dienophile should have an electron withdrawing group. So this you can design like this. So play these two as here, as I told you. You make this bond here and make this bond here, get it, and diene will be formed and make this here, and you will get acrylate and acrylic acid. From that ethylation, you will get this product. These two on mixing at 90 degrees centigrade and heating, you will get this ethyl ester. And this ester on treatment with two molecules of phenyl magnesium bromide in a single step, you will get the target molecule as designed. So this is one thing. This is quite interesting. Another one. Why I am showing here is it's also having a six-member ring with a double bond with an alcohol. Why I have chosen this particular problem is to introduce you what is meant by functional group in interconversion. At the very beginning of my talk, I told you I will introduce what is meant by functional group interconversion in the definition part. So FGI, the operation of writing one functional group for another. Suppose if you are traveling from from Chennai to Madurai, and from there you have to go for some other small village. And you know the way from Chidambaram to Madurai alone, either by train or a flight or by a car or even by a bus. And after reaching there, you have to enquire some person which town bus is going and which way I have to lead towards the nearest village. Likewise, you know the retrosynthesis from this point of view, you know the retrosynthesis of a Diels order reaction, as I introduced just now, for any Diels order reaction, just I introduced you. But here, the stereo electronic control for a Diels order reaction is not satisfied because if you cleave this molecule, you will get a dienophile with electron releasing group. This kind of problems only appear in CSAR. Electron releasing group as a dienophile, the Diels order reaction will not take place. So even the target molecule is given as an alcohol, primary alcohol. What you have to do is you have to write a symbol called FGI and convert this either to an ester or to an aldehyde like this. Because you know how to write the Diels order reaction for dienophile with electron withdrawing group like this, not for electron releasing group like alcohol. After that, what you have to do is, as I told you, you can synthesize this molecule very simply. This either this or this. Okay, I synthesize this. After synthesizing this, I can reduce CHO to CH2OH. Okay, I got the target molecule. Initially, the target molecule is not valid. It cannot be just deciphered or cannot be solved using Diels order. So you are just converting the given target molecule for the purpose of the known reaction, Diels order reaction, by writing a symbol called the FGI, converting into either an ester or an aldehyde, which is supposed to be the electron withdrawing group. Very easily, the Diels order reaction will take place like this. After that, getting this particular product, you can write the reaction towards the target molecule by appropriately choosing the reagent sodium borohydride. The second one is similarly here ester. This can also be converted through Diels order reaction, and then lithium aluminum hydride gives you the product, the target molecule. The irony of the reaction is there are two things. One is the chemoselectivity. What is the chemoselectivity? For any reaction to take place, a chemical chosen as a reagent is called as a chemoselectivity. For reducing an aldehyde to alcohol, sodium borohydride is enough. For reducing ester to alcohol, lithium aluminum hydride is the must. You need not use lithium aluminum hydride for sodium borohydride condition, vice versa. Because for planting a rose at your garden, you need not go for JCB mission to come to your home. Instead, if you are having a small crowbar, that is enough that you can make it very easily. So the necessary condition for reducing a CHO to CH2OH is sodium borohydride, and in aqueous condition also it can be done very easily. But whereas in lithium aluminum hydride it needs a non-aqueous condition, and ester can be reduced by lithium aluminum hydride alone not by sodium borohydride. The second aspect is regioselectivity. What's the regioselectivity? In the case of regioselectivity, it is having another reducible group, a double bond here. Neither lithium aluminum hydride nor sodium borohydride are capable of reducing the isolated double bond. That's the point. So the reduction will take place not at the double bond corner, but at the CHO and the functional group only. This is called as a regioselectivity. So this kind of problems one has to approach by means of choosing things, and you can very easily solve these problems and get into that by practice. Why we have to first study the retrosynthesis of alcohol is special. I got more than 100 problems in that. What I have shown is only 5 problems because want of time. And if you just know the alcohol retrosynthesis by this way, you can get, if olefin is given, that can be first converted to alcohol by FGI, then you can go for olefins. And ether can be deciphered. Alkyl halides can also be as a target molecule given. You can convert them into alcohol and do for alcohol retrosynthesis, and then find the final stage you can you can convert into aldehyde or a ketone. Similarly for acids, and acid derivatives nearly 4 are there: acid chlorides, acid amides, esters, and you have acid chloride, acid amides, anhydrides, and esters. All these can be very easily synthesized if you know the alcohol disconnection. More than 11 to 12 functional group can be very easily sought out in this. So alcohol disconnection is a must as the preliminary study for any student MSc who is studying organic synthesis, particularly who is willing to learn what is called as a retrosynthetic analysis. Next, we will go the application, one application of this. This is an ester. But till now, what you have learned is only for alcohols. But what is given is an ester. Okay. How to go for an ester? You have to think about that. So what you have to do, you have to first write the symbol called FGI. After writing the FGI, convert this acetyl ester into alcohol. After seeing the alcohol, you are interested to see both sides PHCH2 CH2 group is there. Two similar groups are attached. Simultaneously disconnect both similar groups. And you will get PHCH2 CH2 MgBr, PHCH2 CH2 MgBr, because equivalent for that PHCH2 CH2 negative. PHCH2 CH2 negative equivalent is MgBr. You know Mg is having two positive charges in its valence. On one side you are having either Br or Cl, other side you are having a pH negative. So the synthetic equivalent for synthon any carbanion is Grignard reagent, or alkyl lithiums. Ethyl lithium is a good one, Li plus. Rest of the molecule is C2H5 negative, like that. So the center part you have converted into an ester. You have this is C, hydrogen is already there. I told you while you are removing two negative charges from this, you have to introduce one oxygen. I introduce here. Already C is here, H is here, and the O is here. Instead of the hydrogen, I just introduce one ester. This is nothing but ethyl formate. So ethyl formate on reaction with the two molecules of benzyl magnesium bromide in dry ether, you will get the alcohol. Then alcohol is not your target. You have to convert by just adding acetic anhydride. Look at it. You got the alcohol and acetic anhydride. You will get the ester. This is the application. So on seeing the target molecule, your mind with the chemistry brain should think how this can be converted to alcohol. And alcohol, we know only what is needed for a student is knowing the disconnections of different alcohols. Once he know the disconnections of different alcohols, he is capable of synthesizing more than 13 functional groups, which is given as a target molecule in his problem. If I am going fast, you can stop me at any time, ma'am. Okay. Want of time only, I'm just speaking very fast. Next problem is TN10. I just leave it. Can I go ahead, madam, in the same pace? Okay, this.
Yes, sir. Yes, sir.
Okay, ma'am. If because I'm not seeing any screen here, and hence I'm not knowing about the psychology of the students who are hearing it. Now let us see. The next one is the odd-looking molecule is an intermediate drug in the synthesis of an anti-tumor agent called baticin. So this is a precursor for matacin drug. So if you just go ahead with the matacin drug synthesis, making use of this particular starting or a synthesis precursor or an intermediate, on seeing the intermediate, this retrosynthesis is not at all known to you. What you have to do is, I told you, you have to convert into an alcohol. Why? How you can convert into an alcohol? Why? Next question. It is acetal. Acetal is nothing but the protective form of a diol. So what I have to do is introduce the water molecule here, H1 here, here H1O. Now I'll cleave this, convert into an alcohol. Yes, you know how to do for alcohol. This is CH2OH, CH2OH, and an ethylene might is here. So a known reaction from 10th standard level is there. If you take acetylene, add 2 molecules of formaldehyde, condensation occurs in presence of sodium hydroxide to give diacetyl like this. So if you take acetylene, add 2 molecules of formaldehyde in presence of sodium hydroxide, so you will get diol of acetylene. After that, you can reduce the triple bond into double bond and add to this ketone protection, and you will get the acetal. Look at this synthesis. Take the acetylene, take base formaldehyde and formaldehyde, and you will get CH2OH, CH2OH. That is, your formyl groups are attached to the acetylene molecule. Because you know very well, acetylene hydrogens are more acidic. It can be easily removed. Okay. Now you have to reduce the triple bond into double bond to get this target. So you have it hydrogen, palladium, carbon, and it should not go to a single bond level. So you are adding what is called as a catalytic poison. So it's a catalytic poisoned catalyst. We call it as a poisoned catalyst. Barium sulfate, you know very well, palladium and carbon is having a micropores. And the catalytic, the theory of adsorption, you know very well for catalysis. There are one thing is called as intermediate compound theory, and another one is called as adsorption theory, in which palladium is having in its own surface enormous quantity of small active pores, in which hydrogen goes and attaches. That hydrogen just releases this hydrogen, goes to the point of the double bond and converting into a triple bond. So at the initial stage of a reaction for a 60 minutes, you can allow it. After that, you can add barium sulfate, and all the active sites of the palladium will be just sprayed by barium sulfate, small powder. So the active sites are not available for the hydrogen to absorb over it. So the reaction will stop. It is called as we call it as a poisoned catalyst. So you get it. You take a catalyst, you poison it, and you need not no longer need the activity of the catalyst after certain time. After certain time to over with the reaction needed. So the reaction is enough if you get a double bond. It should not go to the single bond stage. So I am adding barium sulfate. I'm adding barium sulfate. Okay. The other one is called as, in the case of SO2 plus O2 giving SO3, a small quantity of arsenic oxide, if is present with the platinum there in the contact process, then that is called as a catalytic poison. So the one has to get more amount of sulfur trioxide to get the sulfuric acid from 2SO2 plus O2 giving 2SO3. One should be very careful in removing the arsenous oxide, which is called as a catalytic poison. Here it is called as a poisoned catalyst. So there is a much more difference. Now you got the ketone, and if you add the ketone to that, your target molecule will be very easily formed by protection. You know about the protection of alcohols, protections of various functional groups, amino protection, alcohol protection, keto protection, thiol protections, acid protection, etc. would have been studied in the second MSc chemistry in the organic synthesis. Okay, you can do it. So which seems to be difficult at first as an odd molecule, but you can decipher it in the logical way of converting into an alcohol and then doing the alcohol reaction and then adding with that, you will get the acetal. Next one is olefins. As I told you, the second part is olefin. So if you are having an olefin, there are two ways you can do it. You are having a 6-member ring with a double bond. First, you forget about Diels order reaction. Other than that, more yield will be formed here. You know about the reactions of 4n plus 2 and 2 pi reactions in the pericyclic systems and also cycloadditions. You know the cycloaddition reactions where is nothing but the Diels order reaction, where the yield will be somewhat low. So you can go via alcohol, introduce water molecule to this, H and OH minus in this fashion. So remove the double bond, add water molecule to this, and you will get an alcohol. You know the retrosynthesis of alcohol. Cleave the phenyl group. You will get here, remove the hydrogen. You will get the ketone plus phenyl magnesium bromide. Okay, because if you consider this as an alcohol, you can cleave one of the alkyl group here, and you got the alkyl group, or even cyclohexyl group also you can cleave, which is feasible. You can go ahead. Cyclohexanone is freely available in your stores, and phenyl bromide is available, and magnesium ribbon you can take in dry ether or THF. You can readily do the reaction and convert this. After dehydration of this alcohol, you can get the either double bond here or here. You will get the product. On the other way, if you add water molecule here, OH here and H here, no helpful disconnection is needed, because if you dehydrate in the final step, double bond, there is a possibility of formation of 50% of the double bond here, which is not needed. Yield will be low. So even at the first sight, on seeing the double bond, how to decipher for a disconnection of a olefin? Add water across the double bond. I added water across the double bond by choosing the OH here and H here and removing the double bond. And I got an alcohol. On seeing the alcohol, I am very happy because I know how to do the retrosynthetic analysis for alcohol. I cleave the phenyl group to get the phenyl magnesium bromide. And rest of the molecule is the synthon, which is having a positive charge. Remove the H plus, I got the cyclohexanone, which is available in my stores. That is one way of adding water molecule across the double bond to solve any olefin given as a target molecule. Okay. Now, I will give you one problem. Well, before that, we will go what is a Wittig reaction. Don't worry about the mechanism. Wittig reaction, that is, you have several mechanism, oxytone, intermediate, etc. You forgot all these things. You just treat it as a mathematics. Whenever there is a double bond is given outside the ring, you see the double bond where it is. And one part of the double bond introduce oxygen, other part introduce PPH3, like that. Okay. Problem is solved. Very simple. Whenever there is a double bond is given as a target molecule for you at any point, in the case of, pheromones, or even in certain alkaloids and terpenoids, in most of the terpenoids, you will be having a double bond, limnone, etc. On seeing this, you can design the synthesis on your own. Cut short the double bond and convert into a ketone and an ylide. What's a ylide? Ylide is nothing but electron deficient, valence deficient. Instead of carbon, you are having a phosphorus. So how you can get the ylide? You can get the ylide from triphenyl phosphine plus alkyl halide. Take PHCH2CH2Br. Add PH3P. This HBr is removed, and you will get a double bond here. That is called as a ylide. Okay, very simply. So take the ylide and simply add to that in the Wittig condition, and PPH3PO is formed. The double bond is here, merged here to get the product. Very simple. So for olefin, you can solve the problem in two ways. Carbon-carbon double bond formation. There are so many reactions. You can simply Wittig itself, Wittig Horner, etc. So many modifications. All are in the same wine in different bottles. No problem at all. You understand the basics. You take a double bond whenever it is given as a target molecule and break the double bond and have convert into one part as an oxygen, other part into PPH3. So this is a CSIR problem. Quite often it is given. In this, you have two things. One is a 6-membered ring with a double bond inside. Another one is a double bond olefin ring at the outside. You can solve either way. Diels order reaction as well as Wittig reaction. How to do that? You cleave this, as I told you, it's a tutorial via A. If you via A means I just put oxygen here. I got PH, CH2, CHO. Here PPH3. Look at it. This is one way. What is via B? I convert this into CHO. Look here, CHO. Put O here and PPH3 here. So, which will give more yield, which is having a reasonable mechanism, which will not take more time to complete, and less tedious. These are all the things you have to think of. Here, if you look at this particular moiety, you feel that there is an electron withdrawing group. The double bond is in opposite. So you can cleave simultaneously these two. You'll get a retro-deal sort of reaction. You can get diene and acrolein. We have already seen as the first example in the first site when I introduced and started this particular lecture. So take butadiene and acrolein. Acrolein cannot be stored, it is highly polymerizable. Whenever you need acrolein in your reaction time in your laboratory, take glycerol, drop sulfuric acid, 1 drop, or even a phosphoric acid or a dehydrating agent, K2SO4, and you will get acrolein very easily. Carry out the reaction by heating at a 90 degrees centigrade. You will get this molecule. After getting this molecule, you get aldehyde and PPH3 ylide. Ylide can be easily got by taking PHCH2CH2Br and PPH3. Understand? So PHCH2Br or PHCH2CH2Br plus PPHC, you will get this. After that, you can just mix it with this and you will get the product. See the synthesis. So PHCH2CH2Br, PPH3, you will get the ylide and take the base and take A. What is A? A is this. Okay. You got it via Diels order reaction. So in the same target molecule, you can do it through Diels order reaction as well as Wittig reaction. It's a classic one example for that. There are several examples, but I just cut shorted. More than 40 examples I am having in this ylide, different types of carbon-carbon double bond formation. Because of want of time, I'm telling you already. I have to justify myself at least for making you to know the one group disconnection, what are all the aspects in that. And we have two group disconnections. We have synthesis, retrosynthesis of small rings, retrosynthesis of large rings, retrosynthesis of exceptionally important compounds, and retrosynthesis of heterocycles, etc. There are so many things, but we know the fundamentals after studying more than 10 lectures. One student need not read what is a rearrangement, what is a reaction mechanism, what are the purpose of different Michael reaction, managed reaction, etc., why they came into existence. You will understand easily. You will not see the reaction in terms of names, but you will see the reactions in terms of the target molecules. Once a target molecule is given, how to decipher, like this. Here you have, even from the 10th standard or a +2 level class, Friedel-Crafts reaction. In this, you have electron releasing group containing a benzene ring, one part. The other part is electron withdrawing group containing a benzene ring. This is also a CSAR problem. So in that, you can cleave simultaneously A. Via A, if you go, you will get this molecule, and you can convert this into N-acyl chloride. Now, on the other way, if you go via B, this is disconnection. You know very well. I'm once again recalling. This approach is called as a synthon approach or a disconnection approach, and nothing but disconnecting certain covalent bonds, converting into starting materials possibly easily. Okay. Next, if you go for B, you will get nitrobenzene and substituted methoxytoluene acyl chloride. In these two, I will give you a clue to you. Nitrobenzene will not undergo Friedel-Crafts reaction. That one MSc student should bear in mind. Why nitrobenzene will not undergo Friedel-Crafts reaction? Nitro group is electron withdrawing, deactivating the benzene ring. You know about the ortho-para-directing substituent and meta-directing substituent, the activation and deactivation of the benzene ring, even in the second BSc level. So the fundamentals are more important. The book which you will get a fine approach in that is Peter Sykes, and you can get into that for ortho-para-directing groups and also influence of ortho-para ratio and meta-substituent groups, etc. So this will eliminate all the electrons here. You will get a positive charge. Here also you will get a positive charge as a synthon, and the reaction will not take place. Whereas here, if you look into it, this will take very easily. More than 95% of the yield will be formed. Because electron withdrawing, here you need more positive charge to react with the proton, and the product will be formed so easily. So that's the point. So this kind of thing, instead of writing and giving you how write the mechanism of a pi intermediate, sigma intermediate in Friedel-Crafts reaction, they will give you different substituents, and those substituents you have to have the mind in it, and reaction pathway and the sequences, then you can answer very easily. This is one problem. So usually I used to neglect. Even then, I want to tell you about this. Here, this is a target molecule given. You look at it, you can consider this as an alcohol. If you consider this as an alcohol, you have two similar groups attached with that. Rest of the molecule you forget. What what if till now from the above slides what I have just slided across, what you will do is you cleave two phenyl groups together, you will get PHMGBr and you convert this into an ester. This ester is an available ester, CH3CO, CH2COOET, ethyl acetoacetate, with two molecules of phenyl magnesium bromide. You will expect the reaction to take smoothly and you will get this. But on the other hand, what is happening now? If you add first molecule of phenyl magnesium bromide between ester carbonyl and carbonyl ketocarbonyl, the phenyl magnesium bromide prefers not to go to the ester carbonyl as a nucleophilic addition reaction. Instead, it will go and attach here. So two molecule of phenyl group in the similar fashion will go. Instead of getting this target molecule as the product, you will get this target molecule. This is the part, interesting part. So you know about the reactivity. The carbonyl group itself, while you are treating with nucleophilic addition reactions like phenyl magnesium bromide, it will prefer, if this preferentially chooses instead of the ester carbonyl, it goes to the carbonyl carbonyl. Then what you have to do, you have to protect. There are two ways of solving this. One is you can protect this carbonyl group, make the phenyl magnesium bromide to attack here, or you can just activate this carbonyl group and don't worry about this. There are two ways. One is called as activation, another one is called as a protection. Okay. So Grignard reagent might first attack the ketone, giving the wrong product. So what you have to do is you can protect this carbonyl group. Why we have to protect? Using a diol, converting into a ketone. So I protected, as we have seen in the case of Matacin as one of the product. I hope that madam will give you all my slides and there won't be any difficulty in just going through and again reviewing it, and you can come to a good understanding. And you get protected now. Now go ahead with the Grignard reaction. You will get the product. Finally, you just hydrolyze it. You will get the target molecule. This is called as the protection. If two groups are there, in which one group is more active towards one reagent rather than the next group, then you have, but you want the reaction to take place on the other end, regio specific. You want to make the reaction to take place only at this point, not here. Okay. And here what you have to do is you have to protect the other part and not activating this part, protecting this part, and then making the reaction to go ahead and you will get the product. Okay. On the other way, you can protect as well as activate. If you take ketone molecule and add a BS and PHCH to Br, you will get PHCH2 will be attaching here one of the carbons, but this reaction will not stop here because you are having an activating group here also. So it won't stop here. You will get multiple products. You go to look at it. You can start even with this. You will get a number of products, but you want only one side getting PHCH2 to be attached. What we have to do, you have to activate the other part, only part where you want the reaction to take place. That can be done by taking, instead of a ketone, take an ester, ethyl acetoester. It's electron withdrawing. Here also electron withdrawing. This is more acidic. Base will attack here and you will get the carbon ion formation here only, not here. Then you will get an enolate. After that, you go for the reaction. Only the stable enolate is formed here. Then you go for PHCH to Br. So that will go and attach the one part of the molecule, then decarboxylate it, and you will get the product. This is called as activation of one point by introducing a group which makes the particular proton to be more acidic and not the other one, to make it very easily susceptible for the reaction to take place, where you can avoid the multiple substituted product in a a bigger reaction vessels. Okay. I just skip all this. So this is an important slide in Synthana approach. If you want to synthesize an alcohol, the COOH can be cut short and converted into CO2. That CO2 can be measured together with RMGBr, and you will get an acid. After getting the acid, acid can be converted to acid chloride. Acid chloride should be converted to anhydride. Anhydride can be converted to ester. Ester should be converted to amide. The point is, this called as a order of reactivity. If you want to, even if you go into the any organic synthesis book, you can see that how the synthesis is being planned. Acid, if an amide preparation is given, uh, they will not convert acid into amide by adding an ammonia. Instead, acid should be converted to acid chloride to anhydride. Anhydride could be converted to ester, acid to ester. It's a reversible reaction, you know very well, by taking with alcohol. The yield will be very, very less. It may be less than 25%. But if you just convert an anhydride into an ester, it is easy. And if you want to have an amide, maybe a secondary or a primary or a tertiary amide, it should be converted through your ester. Ester to amide is so easy. This is called as an order of reactivity. For getting an acid, which is acid derivatives, acid chlorides, acid anhydride, esters, and amide. The reactivity sequence should be followed for any synthetic pathway, not the other way. All will hydrolysis will give back to acids. Okay. So one particular point is if you have this particular amide, what you have to do is cut short here, convert into piperidine, and the other molecule to an acid. This acid, you can just synthesize. This acid is here. You just cut short here, you will get CO2 and you will get MgBr. And you will get the Br here, convert into OH. That OH, pH, CH3, CH2, CH2, CH3, CH2. One side is ethyl, one side is methyl, one side is hydrogen, one side is OH. You know how to do for alcohol. Convert one part into aldehyde and other part into pH, CH3, CH2, CH2, MgBr plus aldehyde. You will get a secondary alcohol. How you can get secondary alcohol? Grignard reagent with aldehyde. How do you get tertiary alcohol? Grignard reagent with ketone. How do you get primary alcohol? Grignard reagent with formaldehyde. This is a basic point that an MSc student should bear in mind that should be useful while you are going to teach one of your friends in the neighbor as a +2 level or a +1 class. They should not be given training in mugging up the reaction, particularly for alcohol, acid chlorides, acid amides, derivative, etc. But if you just give the key points to them, they will learn on their own. This is what is there and what's the basic reaction mechanism in that. Okay. So that's the way you can now design this CH3, CH2, CH2, MgBr plus diethyl ether plus aldehyde and convert into PBr3 bromine and MgBr and add with CO2 in dry ether. You will get an acid, convert it into acid chloride, SOCl2, and add with it pyridine. You will get it. This is the product. So next one is alkanes. Why I have chosen these alkanes? One is aromatic system, another one is alicyclic system. This will occur in large ring molecules, particularly if you are going for steroids and other things. So this kind of molecules has to be synthesized. What you have to do is, on seeing the molecule, you have to scan the molecule. One is aromatic, one is aliphatic. What you have to do is called as a branch point as the gate. When the aromatic system meet the aliphatic system or alicyclic system, you put a point there. In that, you write FGI and convert this into an alcohol or an olefin. I converted into an olefin. After seeing the olefin, add water across the olefin, double bond. I added OH here and H here, not the other way. Here OH, here H. It's OH here and H here. Now I got the alcohol. Cleave this. I got it. I will get pH minus, pH MgBr, CH5 MgBr. This, remove the proton. I'll get the cyclohexanol. So ketone with the Grignard reagent, I get secondary alcohol. Okay. Here, since both the groups are same, it's a tertiary alcohol. Don't worry about it. Cyclohexanone with phenyl magnesium bromide gives a tertiary carbon. So you got this. You go back. Now take this and add to this, and you got this, and remove the OH, rehydrate it, double bond, reduce it, you get this product. See the synthesis. So once again, I go slow. If you are having an aliphatic system and an alicyclic or an aliphatic system with an aromatic system, you take branch point as the gate, where the alicyclic system, where the aromatic system meets the alicyclic or alicyclic or aliphatic, you put a point here. After getting the point and convert that point to a double bond, making use of what is called as a functional group interconversion. What is a functional group interconversion? As I told you, the target molecule is given without a double bond, but you are converting for your convenience to a double bonded one, since you know how to reduce double bond into no bonds. Okay, single bond. Now, this add water across the double bond, one of the strategies we learned for olefins, water across the double bond. And another one is Wittig. You can go via Wittig also, but steps will be more. If the steps are more, it is a linear synthesis. If you are going for a linear synthesis, yield will be only less than 30%. If you are going for a convergent synthesis, the yield will be excellent. Now, go for synthesis. If you go for synthesis, you have the alkane group, PHBr, and you have magnesium and diethyl ether, and you have cyclohexanone, and you will get this moiety, add phosphoric acid, polyphosphoric acid, dehydration, remove water, you will get olefin, and reduce it with hydrogen palladium carbon, you get the target concerned. This one way. This is the way of synthesizing alkanes attached with alkyne, or simple alkanes also you can do very easily. This molecule of interest, this is called as a brufen, and most of the Europeans where the temperature is not exceeding 8 degrees centigrade happen to have always the knee pain and also the bone joint pains because of their sedentary nature and also non-availability of vitamin D3. So they are mostly taking the brufen, which is a safer drug. How to do that? You can do it in the fashion. How to do that? On seeing the molecule, you scan it. While you are scanning it, you are having a benzene ring, isobutyl group, and isopropanoic acid.
Sorry, sir. Sorry,
Yeah,
sir. Your screen is not seen, sir.
there is
Your PPT is not seen, sir.
PTD is not seen.
Yes, sir.
PPT, I don't know. No, it is in the presentation form only, madam.
Ma'am, screen is visible, ma'am.
Visible, Shanti.
Visible.
PPT is visible.
Then what's wrong? Can I proceed?
Yes, sir. Yes, sir.
Okay. So if you look into this particular molecule called a brufen, you have to scan it. You have a benzene ring and isopropanoic acid and isobutyl ring. What you have to see is on seeing the COOH in the benzene ring, you can go via Grignard, either cyanide or Grignard reaction. And you can convert this COOH into, of course, CO2 and MgBr plus CO2, you can get this. You know that. Or you can convert this into CN. Hydrolysis will give CN. That is called as a cyanide or Grignard reagent way. I got Br. That Br can be converted by adding OH group because SN2. After that, I can convert this into reduced to FGI functional group with a ketone. On seeing the ketone, everybody is happy because Friedel-Crafts reaction go easily. Writing the Friedel-Crafts reaction, I get this. But other part also, there are two ways of writing the Friedel-Crafts reaction. One is Friedel-Crafts alkylation, another one is Friedel-Crafts acylation. Acylation is more, the yield of the acylation is more, and so I have to prefer only acylation. For that, I have to convert this particular carbon into CO. I am writing CO. Now I got this, I got these products. Look at it. This is the molecule of want. Pharmaceutical chemistry, we want what is called as a brufen. In this molecule of want, what I have done, you look at it. You have a COOH group attached to the benzene ring and the isobutyl group. And just to cleave the COOH either via cyanide or grignard, I got Br. Br could be converted to OH because I know how to convert OH into Br and Br to CN and CN to COOH. Or I can convert to COOH can be directly cut short, and that will be CO2 plus MgBr. This part I can convert into MgBr, CO2, Grignard, or CN hydrolysis COOH, either way. And this is a secondary alkali group. And functional group conversion, I got it. By reduction of ketone into secondary alkali is easy. After seeing the ketone, I can go via Friedel and Crafts. So I just add acyl chloride on this molecule. Alkylation is there. In the case of alkylation, yield will be less. So I have to go for acylation. I convert this part of the carbon to acyl by FGI. I got CH3 twice CHCOCl and benzene. Now think about the synthesis. If you go via synthesis, take the benzene, and this I got it. CO should be converted to CH2 for a molecule. So what I have to do is, on zinc amalgam, either I can go via Clemmensen or Wolff-Kishner reduction, where I can go via Clemmensen yield is more, and I get CO is converted now to CH2. The part of the molecule is now synthesized. Here I have to go for acylation. I got acylation converted into acetophenone. The acetophenone can be reduced to secondary alcohol. Then adding Br3, I will get Br. Then I can go for magnesium diethyl ether CO2. Directly I will get the brufen. In the same fashion only, the medical the medical industry, all the pharmaceutical industry are synthesizing the brufen till date. This is one way of retrosynthetic analysis going across. This I am giving you to the students as a tutorial. Here I am telling you as an alkane. You have an aromatic system here and an aliphatic system nearby. Look at it. This is aliphatic system. This is aromatic system. And what I have told you, branch point is the gate. Put a point here, branch point, this point, where the aliphatic meets aromatic. And put a double bond here. Write FGI. I got it. Now add water across the double bond. Take water at the OH and H. I am now converting into an alcohol. You have an isopropyl group, one methyl group, and xylene group. Now I can cut short that and convert into Grignard reagent, isopropyl magnesium bromide. Why? CH3 twice, CHBr, isopropyl group, magnesium bromide, negative charge. Rest of the molecule is substituted as stophenone, dimethyl substituted as stophenone, and I can get retro, and you will get metaxylene. I get metaxylene plus acetyl chloride. Look out for the synthesis. For retrosynthesis, I use double-lined single-headed arrow. For synthesis, I use single arrow. You have to remember. So what I'm doing is, once again recalling, and whenever you are taking a molecule, this molecule is a target molecule of interest given to you while you are going for any interview. You have to scan the molecule, and you are seeing that there is an aromatic ring and an aliphatic ring, aliphatic non-cyclic ring, and you just attack a branch point as the gate. In that, you create a double bond, convert into olefin. You know till now from certain transparencies which went ahead, which went just now before some 30 or 40. And for FGI, add water across the double bond, or even you can go via Wittig as you please. And I convert it into an alcohol. I just cut short this bond, convert into isopropyl magnesium bromide. I got a ketone. That ketone, I just cut short here. I got acetyl chloride and metaxylene. So in the reverse of the retro, take acetyl chloride, metaxylene, I will get this ketone. After ketone, I will add with isopropyl magnesium bromide in THF. I will get this alcohol, dehydrate this alcohol, H plus OH minus will be removed, and there is a double bond. Double bond can be easily reduced to single bond, get the target. See here. This is the way. This is the way of moving. So till now, I left so many things because want of time and also want of understanding. Summary: if you have a tertiary alcohol, and you can go via Grignard, similar groups are there. If you are having a olefin, water across the double bond, I can do that. Or you can go via Wittig also, this way. Wittig. And if acids are there, RMgBr plus CO2. Aliphatic acids are there, RBr plus active methylene groups. Carbonyl compounds, phenol crafts. And alkyl, there's aliphatic ketones, you get RBr, like that. Three ways to recognize a good disconnection. Should have a reasonable mechanism, greatest possible simplification, give a recognizable, available, cheap starting materials. And these are all the things. Thank you for giving me an opportunity to be with you to share some of the knowledge gained. And any doubts in that, I'm ready to clear. Any sort of lectures, if you want to have from me, I'm ready to send to Dr. Shanti Madam. You can go into it and you can learn a lot. In my experience, I feel it's a good platform for synthetic organic chemistry for any student not to have any sort of negative thought over the synthetic organic chemistry. You can learn the synthetic organic chemistry in a beautiful, affordable fashion so that you can excel in that. You can write retrosynthetic analysis of any bigger molecule within no time, just like that by taking a, you can go for one of your sister or your brother or a neighbor will have a slate and a bulbum. You take a slate and also a small stick and you can start writing the reaction. Not even you can waste the paper and also pencil or a ink, and you can learn by writing on your own and suggesting and also referring so many books. The books of references are many, but I have chosen from only one book. That book is, I told you, E.J. Corey's book of Art of Organic Synthesis, published in 2009. And it is having a fantastic valuation. More than 10,000 target molecules are there, both pharmaceutical and also which are all given in our syllabus. If any university or a college is taking that book as an example instead of teaching in a regular fashion, the student will excel in organic synthesis. They will know the mechanism. When the mechanism is needed, the student has to know. What is needed is actually how to synthesize a target molecule of very difficult. It may be a cyclic, polycyclic, it may be a steroid or a terpenoid, whatsoever the case. If the student, first of all, erases the fear of reading the organic synthesis in a conventional way by making the student, by writing over the board by the teacher, nearly 28 steps leading towards the morphine, and also 12 to 13 steps for camphor, etc. The camphor, so many molecules I'm having, and synthetic organic chemistry as an example, as several lectures I have in that for macromolecules to micromolecules. These things one can learn on your own. Thank you, ma'am. Thank you for giving me a chance.
Thank you, sir. Sir, can you please repeat the name of the book and the author, sir? Many of them they are asking.
Okay, Art in Organic Synthesis by E.J. Corey.
Priya
Thank
ma'am?
you, sir.
Okay.
Yes, ma'am. Thank you, sir. The session was very interesting and comprehensive in covering all the topics about retrosynthesis. I'm
Sorry,
sure there's a
sorry,
lot
sorry.
more,
I
and
have sorry,
participants
madam.
would.
I haven't covered. I just given the tip of an iceberg, as I told you.
Yes,
But
sir.
one has to go at least for 10 lectures of my own. But if they are going into it and practicing on their own, they need not go and study any of the book. Any target is given to them. They are lenient enough to decipher the things. I have standing examples for that. One of my students is now the vice president of the Gland Pharma and also Reddy's lab, who is getting more than 1.5 crores per annum. Only because he knows the retrosynthesis with me, he is now shining like that. That is the reason.
Very good to know about it, sir. I understand there's a lot more to be done as far as retrosynthesis is concerned, but due to time constraint, you've covered as much as possible in this
Yes,
presentation,
yes.
sir.
Yes,
Thank
ma'am.
you very much, sir.
Thank you.
We can take in questions from the participants. Participants, if you have any questions, you may post it in the chat box. Those of you who are viewing through the live streaming, you have the live chat option where you can post your questions. Sir is ready to answer them. So please utilize the opportunity.
Ma'am, I feel you can leave my email ID to them, and if they are having any doubts concerned with the books and also the lectures, what they need in the form of even the PowerPoints, I'm ready to share, and you can give it to them. That is
Uh,
nothing. Everything is transparent. It is only for the benefit of the students. Now, also, I am preparing a new transparency and also writing a book, how to write mechanism for any reaction given. That will be very interesting. If any reactant, in that way only the CSAR is asking. They are giving a reactant and a product and no reagent, they are asking mechanism. Or they are giving reactant and the reagent and they are asking the product and the mechanism. All these things can be covered by simply how to write mechanism for any reaction given. So I will share it to you, madam, if you are needing it. After completing it, will take another 1 month to complete that. It will be fine and interesting, and that will be good. And along with that, the student is capable of studying the retrosynthesis, and they will certainly pass the CSAR. Only
okay.
by taking 13 units in CSAR in organic chemistry and 4 general units, like how to pass CSAR. If you given me a topic, how to cover the syllabi in CSAR to get a good pass, that would have been a different strategy. Since you told me to take retrosynthesis, I took it as an initiative. The students are not aware and they are just taking into account of all the 37 units in CSAR and studying a lot, and they can leave certain things, they can get good marks and get a pass also even in gate. In such a manner, if you are converting the webinar in the second cycle, I hope you will be continuing this, and in that case, if you are doing it, it will be good enough for the students community and their welfare.
Thank you, sir, for graciously offering to give your mail ID and share the PPT with the participants,
Sure.
and also your willingness to collaborate further to give more lectures, especially with respect to the how to clear the CSIR exams.
That's right. That is what is needed. That is what is needed to not like this kind of lectures to the student. They have to be given training. They're taking into account of each and every unit. There are 37 units in CSER syllabi. In the 37 units, what are all the units and where we have to concentrate and where they are picking up questions is most important one. So those things, if the student is capable of getting an insight into it, and they will be losing all the fears and getting all the confidence out of it, they will just face it just like that and get a pass. That is the point.
Thank you, sir.
Thank you.
Sir, one question from Dr. S. Manivanan has been posted. He would like to know the feasibility of applying the retrosynthesis with respect to the biosynthesis.
Biosynthesis is a different pathway, because if you look into the biosynthesis of any natural product, that is mostly taking place via the reaction pathway is free radical oriented. It is not via heterolytic cleavage. So in most of the cases, what you are doing in retrosynthesis is called as a heterolytic cleavage. There, what they are doing is homolytic cleavage. There is no restriction in application of the retrosynthesis in biosynthesis. That can also be solved very easily. But the biosynthetic analysis are coming out of certain simple evidences got out of C14 isotopic labeling. That is the point. But for all the molecules, the biosynthesis is being, it is not having a confirmatory evidence. In this way, only the biosynthesis of these products, naturally occurring plants and flowers, are doing like that. But once you are knowing the target molecule which is coming out of that, after just extracting things from various ways, we can write retrosynthesis for biosynthesis. Nothing wrong in that. We can write it. Yes, ma'am.
என்னப்பா லைவ் ஸ்ட்ரீமிங் நின்னு போச்சாமா?
No, ma'am.
இல்லையே, நின்னு போச்சுன்னு சொல்லிட்டு எங்க ஸ்டாஃப் சொன்னாங்க. ஓகே ஓகே ஓகே.
Okay, ma'am.
Priya ma'am, proceed ma'am. Priya
Yes.
ma'am. Priya ma'am. Priya Sudha ma'am.
Yes, ma'am.
Please proceed.
Yes, ma'am. In case there are no further questions, I think we can proceed with the session and we're going to conclude it. The feedback link will be provided in the chat box and participants may fill it before they end the meeting.
Okay.
I request Dr. Thamrai Selvi, Assistant Professor, Department of Chemistry, to propose the vote of thanks.
Gratitude is not only the greatest of virtues, but the parent of all the others by Cicero. A very warm good afternoon to all. It gives me immense pleasure to deliver the vote of thanks for day 2 of 8 days webinar series. At the outset, I would like to thank our esteemed resource person of the day, Dr.S.Kabilan, Professor, Department of Chemistry, Annamalai University, who honored our webinar with his gracious presence and delivered highly informative and interesting lecture. A simple presentation for very complex concepts is worth mentioning. I would like to extend our heartfelt thanks to our management, Punjab Association, for the constant support. Thanks are due to our beloved principal, Dr. R. Shanti, for her support and encouragement to make this a success. I would like to place on record our sincere gratitude to Dr. Jayashree Ghosh, Director, Management Studies, Adarsh College, for being our pillar of strength throughout. This would not have been possible without the technical support provided by the Department of Computer Science. May I extend our sincere thanks to the team. I would like to thank all the participants for the overwhelming response and for making this day of webinar a grand success. Thanks are due to our head, Dr. Shanti, who envisaged this webinar series, and all the faculty members of the department for their tireless effort and enthusiasm shown during these testing times while coordinating from their home. Thank you, one and all. Again.
I take this opportunity to thank Mrs. Shobna Premlata for introducing the speaker and Dr. Thamrai Selvi for proposing the vote of thanks. Participants, make sure you're filling your feedback form, which has already been posted in the chat box, before you end the meet in order to receive the certificates. And similarly, those of you who are viewing through the YouTube stream, make sure you're filling up. It's there in the live chat, so you can fill it up there.
Yeah, ma'am.
So yes, ma'am.
Tell them about next week's Fridays and
Yes, ma'am.
Saturdays.
We'll meet again on 24th of July for day 3 of the webinar series. Dr. S.R. Dept, former head and professor, Department of Chemistry, St. Joseph's College, will present on the topic Applications of IR Spectroscopy to Metallic Carbonyls. Thank you all once again and have a great day. Thank you, sir, and thank you all participants for joining us for today's webinar.
Stream கொடுக்கலாமா கிறிஸ்டல் லைவ் ஸ்டாப் பண்ணலாமா கேளுங்க
Yeah, ma'am.
Yes, ma'am.
Ask Jasmine to stop the live streaming, ma'am.
Shanti ma'am.
Jasmine.
Shanti ma'am.
Yes, ma'am.
Yes,
Shanti ma'am.
Crystal, சொல்லுங்க. Crystal ma'am, சொல்லுங்க.